Okay.
Good morning, everyone. Today we are going to present a research paper on adaptive traffic light control with deep reinforcement learning. This study evaluates the impact of adaptive traffic light control on traffic flow and energy consumption in urban environments. First of all, let me give you an introduction about this study. Next. Urban traffic congestion is a major problem in cities worldwide. It leads to a longer travel times, increased fuel consumption, and higher levels of pollution. To counteract these problems, traffic light control is a significant research area with various methods. Next. The first method is green wave controller. It is a fixed time system where traffic lights along a stretch of road are programmed to change their green lights in sequence. It has some limitations such that it can be implemented for one primary flow direction at a time. It assumes traffic flow is relatively steady and does not have the ability of adapting to current traffic situation. Next. The second method is adaptive traffic light control. It can adjust the traffic light based on the real-time traffic situation. However, implementing this system is very challenging due to high-dimensional state space, stochastic, and non-linear behavior. Next. Therefore, reinforcement learning is a very useful approach in adaptive system due to self-adaptive nature and ability of deriving complex control strategies in highly dimensional environments. Most of the reinforcement learning-based studies are conducted on synthetic scenarios and often lack of comprehensive models to predict energy consumption. Next. To address these gaps, this research develops a traffic light control system using proximal policy optimization. They made a comparison between adaptive and fixed-time control system. They also provide an accurate portrait model for predicting carbon dioxide emissions. Besides, they have conducted an in-depth analysis of interactions between traffic light control, vehicles' trajectories, and resulting effects on powertrain. That's all from me. I'll pass to Dongjing.
Okay. The session 2 is to introduce the models for realistic urban traffic simulation. So there will be two objectives. The first one is to simulate a real traffic scenario, and the second is to estimate energy demand and the carbon dioxide emission. So next, before we start the objective 1, we need to select a city as a simulation object. We need to consider a lot of characteristics. It should have successive signalized intersection, have a feature of typical inner city, and so on. These are the reasons why the paper selects the city Aachen in Germany. For the next page, we want to compare the fixed time and adaptive traffic light control. The most important part is a single traffic light will be influenced by surrounding traffic light. You can see the figure on the right. The central traffic light will be influenced by the other traffic lights around it. So the solution is to consider a large area and let the traffic lights as independent as possible from the surrounding traffic lights. The next page. And for the fixed time traffic light, there were two types of intersection. One has 3 phases and the other had 4 phases. But they both have a circle time of 90 seconds with the yellow phase is 3 seconds and the red and the green phases varying during the time of day. So next. Now you can see the figure of traffic simulation. We choose the central 3 traffic light as test subject. The blue one is fixed time traffic light, which is used to reduce the surrounding influence. And we need to know the inflow rate for each line. So next page. The other measures the traffic flow for a duration of 20 minutes in the morning from the inflow A to Q. And the model follows the same inflow probability as measured. So that's all for my part. Now I will pass to Wei Chen to continue.
So hi everyone, I'm Wei Chen. So I will be continuing with this microscopic consumption modeling. So first, the detailed powertrain model for ICEVs and EVs, which is internal combustion engine vehicles and electrical vehicles. So these two, they will be model using, for EV, it will be using MMPE VEM model using Sumo, and for ICEVs is using the TraceCI. So as background is considered, a rising market share for EV is expected. The distribution of vehicles of EV is 2.7% now, and including hybrid EVs. As for ICEV is 97.3%. So the conventional method for energy consumption measurement, which is propagation energy to the wheels according physical energy flow is not accurate for EV and hybrid EVs. So backward modeling approach will be better, which infer the instantaneous energy consumption from vehicle motion. So next. Okay, here we can see that the energy consumption calculation for individual vehicles. Here is the ICEV's powertrain topology. So the calculation process involves the vehicle dynamics data, such as velocity, acceleration, road slope, to compute the force at the wheels. And this force will be used to determine the torque and rotational speed, which are propagated through powertrain components such as differential, clutch, and manual transmission. Okay, okay. Next, here will be the validation results for the models against real-world measurements. The model are validated against real-world data to ensure accuracy. For ICEVs, the validation involves comparing model predictions with type approval uh, information and transient driving cycle tests. For example, validation is provided for a Smart for 2 vehicles using data from a chassis dynamometer test in the worldwide harmony light vehicle test cycle WLTC. The model instantaneous fuel flow prediction closely matched the real world measurement with a root mean square of 0.132 G-S. Okay, G per S. Next, I will pass to Oscar for the methodology part.
All right, thank you, Richard. So now I will go through the methodology part, which consists of algorithm, problem formulation, and model architecture. First, the algorithm used in this study is proximal policy optimization, which is also known as PPO, and it is model-free and on-policy algorithm. Previous studies also show that it is robust to the choice of hyperparameters, but it is actually inefficient in sampling a trajectory. But this problem will be compensated by the low computational cost of the traffic simulator Sumo. And PPO has actually two variants, which is PPO with penalty and PPO with clipping. The equation below is the objective function will be optimized in the algorithm. Next. So here is the pseudocode for PPO with penalty, where KL represents KL divergence, which is used to measure the differences between two probability distributions. Beta is actually a parameter used to expand or reduce the trust region in which meaningful policy updates are allowed. Next. Yeah, the figure below shows the pseudocode of PPO with clip. So this variant will restrict the policy update range, and also this will help to ensure that the gradients will become zero at those range to neglect advantage that are associated with too large policy updates. Next. So this study formulated the problem into a deep reinforcement learning problem with 6 states, including detailed traffic information, time elapsed since last signal change, and current phase of each intersection. At the same time, its actions involve selecting traffic light phase for 3 intersections, corresponding both the phase order and duration. Next. Now we will talk about the reward function design in this study. The researchers fixed the episode length at 1,500 seconds and try to reducing carbon dioxide emission and travel time. Therefore, the final reward function consists of 3 main components, which are velocity, power loss, and phase switching. The 3 F's in the equation are actually the weights for each component. Next. All right, here comes to the model architecture used in this study. So there are actually 2 networks. One is policy network and another one is value network. Both networks have the similar structure except their output layer. Both networks are also trained with the same optimizer, which is Adam optimizer. All right, next I will pass the presentation to Vivian.
Okay, so now I will proceed with the results. Next. In the base scenario, the author has split the results into 3 main parts: training, validation, and comparison of fixed time and adaptive traffic light control. Next. In this experiment, each training iteration consists of 20 episodes, which are 20 separate traffic simulations. The figure on the left shows the training results in the base scenario. The results shown here are obtained using the best performing agent with 56% power loss weighting in the scenario simulation described above, also known as the base scenario. As the agent is mainly exploring at the beginning, the share of power loss outweighs the velocity share in the reward function, leading to obtaining negative rewards. We can also see that at roughly around training iteration 39, the agent reaches the peak performance. Next. For the validation results, the model is tested in 30 simulations initialized with different seeds, and to achieve a balance between the travel time and CO2 emissions, several training runs are conducted by the author with different weighting between rewarding a high average velocity and penalizing power loss as shown in the figure on the left. Each point represents the performance average over 30 validation episodes, and the best agent is the one with the green star, with power loss weighting of 56%. Next. The next figure is a comparison of fixed time traffic light control and adaptive traffic light control. We can see that from the mean velocity, the adaptive traffic light control has the strongest impact on inflowing edges compared to the baseline. The variance is also much lower on most inflowing edges, as we can see that the blue boxes are shorter than the gray boxes for the mean velocity for inflowing edges. This indicates more uniform trajectories and less dependency on arrival time of each individual vehicle. From the diagram, we can clearly conclude that the main improvement is obtained at the inflowing edges compared to the other three. This is mainly because outflowing edges and junctions show the least dependency on traffic light control mode, as vehicles are already close to their desired traveling speed and have already navigated through the main part of the controlled area. That's all from me, and now I will pass to Yijun.
Thank you, Vivian. My name is Yijun. In the next part, I'll be introducing the case study of this research. This case study aims to determine the effectiveness of adaptive traffic light control in improving the traffic flow and reducing the energy consumption under different traffic densities. It is basically the simulation of actual road conditions under different traffic densities. So for the case study set up, there will be a comparison between two controllers, which is the adaptive controller that use the reinforcement learning agent and the traditional fixed time controller. The two controllers will be evaluated based on two criteria, which is the total carbon emission and the average speed of the traffic flow. And these two controllers will be tested under different traffic densities condition. Next. This page shows the result of this case study. So from these two pictures, we can observe that in terms of average speed, the fixed time controller remained relatively stable under different traffic densities. For the adaptive controller, the agent performed very well under low traffic densities, but the performance reduced as the densities increase. This is due to the reason that at lower densities with less vehicle, the agent can reduce the period of waiting phase, hence smoothen the traffic. And for the carbon emission, for fixed time controller, the emission increased in proportional to the number of vehicles. For the adaptive controller, at lower traffic densities, emission will be lower as the vehicles are less needed to brake in the middle of the traveling. So it can conclude that the adaptive controller can improve the traffic flow at lower traffic densities. Next. In conclusion, the PPO-based agent with discrete action space successfully learns a control strategy that outperformed the fixed time schedule by 41% in terms of average velocity without any drawbacks in CO2 emission. Besides that, the dynamic vehicle trajectory can increase engine efficiency and reduce travel time. Also, the traffic flow improvement and energy saving potential is discovered in low traffic density condition. Next. For future studies, it is recommended to include other traffic participants in the simulation and their appropriate weighting inside the reward function. Besides, it is encouraged to consider driver behavior for the controller. Lastly, it is also necessary to quantify the impact of the increasing electric vehicles penetration rate on the agent control strategy. So this is the end of our presentation. Thank you.